All right. Good. So I'm really excited to welcome you all today for today's Grasp on Robotics talk series. I'm Cynthia Sung. I'm the faculty host for today's talk. And very pleased that we were able to welcome Professor Max Schwager to be our speaker. So as a quick reminder before we get into the talk itself, this talk is being shared with you all in person and also through Zoom. Previously recorded talks can be found on our YouTube channel and our website. If you are joining over Zoom, you should feel free to submit your questions over the Q&A button at the bottom of the screen. And there will be a time at the end of the talk where our panelists will look at the Q&A panel and assist with asking your questions. If you're here in person, of course, you should feel free to ask your questions in person. Just raise your hand and someone will bring you the microphone. Please wait until you get the microphone so that people over Zoom can also hear your question. And so today we'll be having two wonderful panelists, Aurora Chen and Yuezhen Tao, who will be helping us to moderate those questions today. So with that, it is my very great pleasure to introduce Professor Max Schwager as our speaker for today. Professor Schwager is the Associate Professor of Aeronautics and Astronautics at Stanford University, where he directs the Multi-Robot Systems Lab. He does a lot of really interesting work in distributed algorithms for control and perception and learning for groups of robots working together for different types of tasks, including exploration, mapping, surveillance. I first met Mac when he was visiting MIT, and he gave me a lot of really great advice about how to think about these sorts of distributed systems, how to think about exploration, and was really a big inspiration behind some of the work that I did. So I'm very excited to see what new work he's done since then. He obtained his bachelor's degree from Stanford, his MS and PhDs from MIT, and then he was a postdoctoral researcher briefly here at the Grasp Lab before moving on to create his own group. So he's received multiple awards, including the NSF Career Award, the DARPA YFA, and numerous Best Paper Awards. So I think from that list of accolades, you can tell that he's been very prolific and also a big impact on the field. So really excited to welcome you. Please help me in welcoming Dr. Schwager.
Thanks. Great. Thank you, Cindy, for a very nice introduction. And it's really wonderful to be here. This is the first time I have been on this side of the stage. I've been on that side of the stage several times and have really fond memories of my time here as a postdoc. And I haven't been back here for years. COVID happened and kids happened, and it's just great to be back here. So I'm going to talk today about some research that we've been doing in my lab, which is quite different from the research that I've typically been doing. This research is all about basically machine learning driven 3D perception and building a new autonomy stack for robots around 3D perception. So I'm going to be talking a lot about NeRFs, a lot about GSplats, and we'll go a little bit into the details of what those models are. Many of you have probably heard those names thrown around a little bit, and maybe some of you are much more familiar than others with what those models are. But let me first motivate the talk by sharing a little bit about my kind of vision and sort of high-level motivation for why I'm interested in these models. So basically, I think that robotics, to really have full autonomy, to have the ability to really understand the 3D scene semantically, visually, geometrically, and so on, we need more powerful world models. So this concept that I'm talking about, 3D world model, it's basically a model that is both visually realistic. So this is the piece that we get from NeRFs and GSplats, is really high degree of visual realism. What you're looking at is just renderings from a 3D model, not real images, not real photographs. But we also want true geometry represented in our world model so that we can reason about safety and we can plan safely through the environment for our robots. We also want semantic understanding embedded in our model so that we can give our robot instructions in natural language, and those robots can make sense of the instructions and ground them physically in the world. For example, here we had the instruction for the robot to go to a microwave, and you can see the microwave is lit up in red, and I'll talk a little bit about how that happens. And then looking a little bit further into the future, we'd like to be able to make sort of dynamical forecasts about what will happen in the world when the robot takes certain actions on the world. So this is shown with this kind of conceptualization of throwing the Stanford bunny and watching it kind of slide and bump around on the floor. But you can imagine you might want a robot to come into its environment and be able to make decisions about how to move things around or what might happen as a consequence of its actions. So yeah, let's follow through that motivation a little bit more. So people are crazy about humanoids these days, I guess. So we're going to motivate this with the idea of a humanoid. We have the Atlas robot. And the Atlas walks into a room and sees an object of interest, the Stanford bunny, takes some images of the bunny, and builds a 3D model of the bunny. So this is all can be done with sort of current technology very quickly, actually. Builds a high-fidelity visual and geometric 3D model of the bunny. And then suppose the Atlas is equipped with pre-trained vision language model codes. If you're not familiar with that concept, I'll talk briefly about it. But basically, a way of associating pixels in an image with language meaning of those pixels. And then we can distill those codes into the 3D model to ascribe semantic meaning to the bunny. And then we can also, given that semantic meaning, make inferences about the physical properties of the bunny. Is it heavy? Is it light? Where is approximately its center of mass, and so on. And then we have all we need to do some dynamic forecasting, some action condition dynamic forecasting. So Atlas might say, all right, well, what if I throw a ball at the bunny? I don't know why Atlas doesn't like bunnies, but suppose he wants to throw a ball at the bunny. He could potentially, in his imagination, predict what would happen if you threw a ball at the bunny. And maybe this isn't exactly the outcome he was looking for. Maybe he's got some reward function. Maybe he's got some natural language instructions given to him by a human. So he can revise his plan. What if I throw the bunny at a ball? What might happen? So the idea is to basically have this fully perception-driven, on-command world model that you can use for dynamic forecasting, both for doing planning and for policy optimization. This is the high-level vision that I'm hoping to communicate. So I'm really going to talk about three thrusts of research with multiple papers under each of these thrusts. One is basically designing safe navigation algorithms around these 3D models. The other one is designing manipulation pipelines for robot manipulators to pick things up based on natural language commands and move them around. And the last one is training visuo-motor policies. So basically using these 3D world models as playgrounds, as sort of high-powered supercharged simulators to train end-to-end visuo-motor policies, which then you can run in robots in the real world to do real-world tasks like navigation and language-commanded goal finding and so on. So before we get into the research, I want to give a little bit of background on the state of the art of these tools involved, because this this brave new world of sort of deep learning-enabled, AI-enabled robotics moves very quickly. So we have a lot of catching up to do to understand the state of the art. So, my concept of world models here is really just kind of an extension of our typical concept in robotics of just 3D models, geometry models, right? We've dealt with 3D models in robotics for a long time. I'd say we have basically three broad categories of representing 3D geometry in robotics. So we have the triangular mesh, which is really not super common in robotics, but it's, I would say, the gold standard from computer graphics and from computer vision. And if any CGI film that you've seen is going to be based on triangular meshes. So there's a super mature and powerful pipeline, computational pipeline for rendering animations with 3D triangular meshes. But in robotics, they're not used often because it's hard to generate 3D meshes from on-robot perception, from raw images or raw LiDAR. And it's hard to correct 3D meshes when things go wrong. And that, robotics is all about dealing with uncertainty, backing out from your mistakes and being able to correct mistakes and so on. So we typically use either point clouds or voxel grids, right? And both of these are kind of dual representations. Point clouds are very sparse in terms of they don't actually fill any space. Voxel grids are kind of over approximations. They fill too much space. Point clouds are great when you're dealing with raw data from LiDAR scans or RGBD sensors or whatnot. Voxel grids are great if you're planning because you can make safety guarantees and plan efficiently. So we've already got a mature pipeline in robotics based on these two representations. Why do we need a new one? So neural representations came on the line in 2020. I mean, one could argue that they've been around for a lot longer, but I'd say the biggest recent splash was in 2020 with the proposal of the NeRF concept, neural radiance fields. And so I want to communicate in this talk that I'm not proposing that neural representations should replace any of these other methods, but they should be a new tool in the tool set for roboticists. And in some sense, neural representations are, let's say, a generic representation from which other representations can be derived. So given standard software pipelines, we can take a neural representation. So an example of a rendering of a neural representation is here, right? This is Stonehenge. We can extract a triangular mesh point cloud or a voxel occupancy grid from the neural representation. So we can, it's in some sense a master representation. They can be trained entirely from RGB images in a very streamlined fashion using the existing sort of machine learning PyTorch ecosystem. So they dovetail very cleanly with existing AI and ML tools. And they produce beautiful imagery. So if we have onboard vision, neural models give us a way of, let's say, predicting what images we're going to see for localization and for many other purposes. So they provide this sort of really lifelike imagery generation potential that these other models, point clouds and voxel models, don't give. Also, they can very easily be embedded with other kinds of information like semantic codes, and I'll talk about grasp affordance codes and things like this. So they're highly extendable as compared to these other models. So, right, so let's talk about the details of these neural models. How are they different from existing models? How do they work? So I'm going to start with neural radiance fields. And by the way, I'm going to be giving a lot of references in this talk, and my convention here is that if the references are in blue, they're not mine, they're not from my group. If they're in black, they are from my group. So this paper, the landmark paper, one of the most highly cited papers in all of computer vision in the past few years, many thousands of citations, is the original NeRF paper, and it basically proposed a really simple idea. It's like, says, suppose I have a bunch of images, regular RGB images, and the poses of the camera that took those images. The poses are important. Oftentimes, they're kind of swept under the rug. So you have the images and the poses. How do I train a neural model such that I can render new images from new camera poses where those images look very lifelike? That's the overarching goal here. And the way this works is that you basically train a neural model to represent the volumetric light field. And it's trained by rendering fake images and then looking at the true images and comparing the difference between the two. That's photometric error. You just look at the pixel-wise difference between the two, and that's the training loss. So you backprop through everything and tweak all the weights of your neural network until the rendered images look like the real images. So let's go into a little bit more detail. This neural network, what it does, I said it represents the light field. So basically, the function that it represents takes in a query point in the 3D space and a camera viewing direction. So your point is here, your camera is here. What does the point look like from the camera? And then the model spits out the density of the point, which is basically like a probabilistic occupancy measure. How likely is there something located at that point? And then if there is something located there, what color does it appear to your camera? That's it. It's a very simple idea. So it's a volumetric field of density and color. Now, the real magic behind NeRFs is the way that you computationally render images given this volumetric color and density field. So this is called volumetric ray tracing, and in particular, the innovation in the NeRF paper was providing a differentiable volumetric ray tracing pipeline that allows you to backpropagate through the image generation process into the weights of this model. And the pipeline is very simple. So basically, right, suppose you have a trained NeRF model, this volumetric field. You pose your camera at some desired location where you want to generate an image that the camera ought to see there. The way that you generate the image is you computationally draw a ray from the center of your camera through the pixel that you're trying to image. You produce the image pixel by pixel. So trace a ray through the pixel out into that neural field, and then you sample the neural field along the ray. And those sample locations give you the 3D point and the viewing direction, right? The 3D point is shown there with the circles, and the viewing direction is shown with the angle. And then the model gives you the density and the color, which is the density is represented by the size of the disk, and the color is shown on the disk, right? And then the rendering basically just does a weighted average. There's a little bit more nuance there. It's kind of some conditional probabilities about what's the likelihood that the ray passes through the volume between the the query point in the camera in order to make it to the camera, but essentially it's a weighted average. And so in this example, right, the expected color to be seen on that pixel is this kind of gray. And if you do that over all the pixels, many, thousands of pixels in the image, you get extremely lifelike images. And the surprising thing about the NeRF paper wasn't the model. The model's simple. It's how well it works. This is how well it works. So these are images from the original paper. Nobody took these images with a camera. It's entirely synthetic, produced from the model. What's also surprising, and what mostly interested me as a roboticist, is how lifelike the structure is that's somehow represented in this neural field. So this is a depth map, which you can also render with a similar kind of rendering pipeline. And you see that there's lots of realistic structure. It's not just producing pretty pictures by accident. It's doing so by faithfully representing the 3D geometry. So back in 2020, I saw this result. A lot of people saw the result, of course, and immediately my mind went to, great, how are we going to use this for a map representation in robotics? And that has basically driven a lot of the research in my lab since that point. So then a couple of years ago, about a year and a half ago, I guess, there was a major advancement in the art called Gaussian splatting. Same philosophical idea, but the main change is in the underlying parameterization of the field, the light field, and also the rendering pipeline. And basically, right, the original parameterization was with a neural network, where it was very hard to understand how the weights of the neural network influence individual points or individual pieces of volume in the world. And so that made it difficult sometimes to deal with NeRFs for robotics applications, for example, to segment out objects or to reason about the spatial relationships of objects in a scene. So the Gaussian splatting idea basically removes the neural network. There's no neural networks in Gaussian splatting, and replaces it with a bunch of Gaussian primitives, which are really just ellipsoids. They're called Gaussians, but they're really just sort of range-limited Gaussians. They're ellipsoids. They're parameterized by mean points and covariance matrices, as ellipsoids are. And also spherical harmonics, which are, no need to get into details, are basically a way of representing how the appearance of that Gaussian changes from different camera viewpoints. Because you want that to represent really realistic visuals. Right, so then stored on these Gaussians, you basically have the same kind of a field. So you have a map from a query point of viewing direction into, instead of density, you have opacity, but it's roughly the same thing, and then radiance, so this RGB color. Now, sort of the secret sauce in Gaussians, in Gaussian splatting, aside from the Gaussian representation, is this new rendering pipeline, which makes Gaussian splatting way faster to train and way faster to render. So the original NeRF back in 2020 took several seconds to render a single image and took many hours to train on a big, powerful GPU. So it really wasn't appropriate for robotics. Many advancements were made under the NeRF paradigm, but now under the GSplat paradigm, we can train a GSplat model in seconds. Within 10 seconds, you get a fair GSplat model. Within 30 seconds, you get a really good one. And you can render GSplat images at 100 hertz easily on a commodity GPU workstation. So now we're in the territory where it's a useful robotics tool. And I don't think it's important to get too much into the details, but the secret sauce, as I said, behind Gaussian splatting is the image generation process, which is called rasterization. Where I said in NeRFs, you have to go through and sample all these points along the array, pixel by pixel, and you have to iterate over all the pixels. You can parallelize in the GPU over samples along a pixel and over pixels, but there are limitations. Essentially, you have to do lots and lots of queries of your neural network. In Gaussian splatting, instead, you take advantage of the geometrical property of ellipsoids, where you can project a 3D ellipsoid onto a 2D plane analytically, instantly analytically. And then you can deal with the camera perspective projection with a linearization trick. It's very simple. So at the end of the day, you get basically analytical curves that represent the projection of your ellipsoid onto the image plane. Those are splats. You think of it like the ellipsoid is like this gelatinous thing, and you throw it on the image plane and it splats. It's the projection. That's why it's called splatting. And then the image generation is also called rasterization, or splatting, same thing, where basically you compose over lots of pixels at once. You compose the image, the projection of these Gaussians one on top of the other, and you order them based on how far away they are successively from the image plane. And then you do the same kind of conditional probability trick that you do for NeRFs, and you get an expected color. But you get the expected color over all the pixels at once through this analytical projection. So you have way fewer queries to your neural network, which means faster training, faster rendering, everything. Cool. So now we're getting serious. Now we can do something with robots. Now, the last tool I want to talk about, which has been really pivotal, is embedding semantics, pre-trained semantic codes into these models, both NeRFs and GSplats. So I'm highlighting a few works here. This is all fairly recent. So 2023 and 24. 23 was when the tools emerged to do this for NeRFs. 24, just last year, less than a year ago, is when they emerged for doing it with GSplats. And basically the idea is, right, you have this model that already spits out an opacity and a radiance. You have it spit out something else, which is a semantic code. Semantic code, you think of it as some pre-trained thing that holds a bunch of semantic meaning about the cluster of pixels that the model was trained on in that region. And I'll get into a little bit more detail, but it's just like a multifunctional semantic code, a summary of all the semantic meaning of that Gaussian. And it lives on the Gaussian. And then you can query your map at runtime with open world queries. So this is an example from, I believe, the LeRF paper, where they pre-trained the NeRF model of this tabletop scene. And then after training, they said, OK, show me the toy elephant. And basically, by looking at the alignment between the query, toy elephant, and all the semantic codes embedded in the environment, you get a heat map. And that heat map, as you see, very nicely illuminates the toy elephant. And the open vocabulary nature is really important. Any query could have been issued. And if you query for something that's not in the scene, you will get, not very well illuminated scene, but the higher the alignment is between the query and objects in the scene, the brighter they appear in terms of I should say, the more red they appear. Okay, so now we have a way of linking or grounding language into the 3D world. And now it's getting quite interesting for robotics. So just to give you a little bit more background about these vision language codes. So there are several out there. There's Dino codes and some others, but the kind of canonical one is called CLIP, Contrastive Language Image Pre-training. It's an OpenAI model from several years ago. And the way it works, basically, high level, is trained on internet scale data. You train an encoder that encodes text into a vector. You train another encoder that encodes images into a vector. And those vectors are trained to live in the same vector space so that they can be compared with cosine similarity. The higher the cosine similarity between these two vectors, the better alignment there is between the text and the image. The better the image matches the text and the text matches the image. And that's it. It's a simple idea. And so the way that these things are embedded in 3D models is these codes are big. I think they're 128 dimensional. There are different versions of CLIP, so some are smaller, some are bigger, but the one we use has 128 dimensional codes, too big to distill into GSplats. So instead, what we do is we train an autoencoder which reduces the dimensionality of these codes down to 16 dimensional. It's flexible. You can choose the dimensionality, but we use 16 dimensional. And the idea is that because we're only caring about the semantics in the model that we've just trained, it's a restricted set of semantics, right? So we just need to be able to distill the semantics as pertaining to this scene into a code. So we can get away with a much lower dimensional code. We don't need to represent the entire internet of semantics, only the semantics as they pertain to this scene. And then once we have the 16-dimensional code, we basically supervise the training of that code, just like we supervise the training of the light field into 3D, we supervise the training of a code field, a semantic code field, into the 3D. So it works in the same way. And here's some example of some results. This is our sort of homebrew version of semantic Gaussian splatting. This is unpublished. So we've queried for microwave, and you see you get sort of a volumetric, the camera's jittering around here, but you get kind of a volumetric glow around the, around the microwave. Similarly, penguins. There happen to be some stuffed penguins sitting in the chair in the scene. They've kind of gone out of view, but I think you saw it before. Anyway, what you see here is that it's pretty good. It's a little blurry. There's some artifacts and so on that we'll have to deal with, and I'll talk a little bit about that later. But it's pretty amazing that you can now query your map for anything of interest, and your map will tell you where it is. Okay, and then finally, online training. You might say, but these models take forever to train. There's no way they're going to work for robotics. They're not fast enough, and so on. So in fact, we can train these models online. That was a concern back in 2020, 21, 22, and so on. But by now, it's completely standard technology to train these maps online. So here's a paper that we wrote for a NICRO workshop back in 2023, where we stuck a pre-existing SLAM together with pre-existing NeRF training. That's why it's just a workshop paper. And we wrote a ROS package around this. It's called NeRF Bridge. You're welcome to use it. I highly recommend it. And it allows you to train NeRFs online in real time from robot data. Not on the robot. You still have to train them on a GPU workstation. If you have a big robot that can carry that kind of compute power, that's great. But we train this with a drone. So you see here's the first-person view imagery from the drone. It's being manually piloted. And then this is the fidelity of the NeRF as it's being trained. And then once it's trained, you can fly your virtual camera around and investigate. You can also get depth maps. There's a depth map. So you can navigate with respect to the NeRF. You can do this outdoors. So here's a facade of a building and so on. So yeah, this is now fairly standard technology. We've done this NeRF bridge for NeRFs. We also have splat bridge for splats. We've also done it multi-robot, multi-device. This is called Hammer. It's under review currently. So you should consider this all standard technology. I'm almost done with the background section. Okay, so great. Now, how have people used these tools in robotics? There has been a lot of work, quite a lot of work already in robotics. I'd say the earliest work took place in the SLAM world, basically figuring out how to combine SLAM with NeRF training and then later GSplat training. So the work that I just showed is the one in black here, which is one of the early works doing NeRF-based SLAM. There are a few that came before, many that came after. And now most of the works are considering GSplat SLAM. It's quite mature. Several people have considered planning, navigation, and control built on using NeRFs or GSplats as an underlying map, and I'll talk about some of that in today's talk. I'd say the first example of that came from my lab. It's a work called NeRF-Nav, an RIL paper back in 2022. There's been several works lately, some wonderful works coming recently out of the GRASP lab, actually. So these last two papers, RT Guide and Atlas Navigator, are both basically doing active exploration built on GSplat maps. And the Atlas Navigator does guidance with semantics as well. Super cool work. And then in manipulation, I think right away when people started seeing NeRFs, they realized, well, if we can just get the NeRF for a particular object, we can use that as a geometry representation to do manipulation. And that work started emerging in 2023, actually in 2023 Coral, which was just over a year ago, because Coral happens late in the year in December, November maybe. The two of the best paper finalists were the first papers to present NeRF-based works for robot manipulation, and then finally the best conference winner was one of those two finalists. And then in this year's Coral, I should say last year's Coral, which was just a few months ago, several works came out doing this on GSplats with semantics, sort of open world, language commanded manipulation based on GSplats. And our paper was one of the original three to do that. Okay, great. So that was background, kind of a long background. But I think it's important to see what's capable these days with the modern tools. So now I'm going to talk about some of the research that we've been doing, talking about navigation first. So we've done a lot of work on navigation, basically thinking NeRF or GSplat as you like. How do you use that as a geometry representation to plan for your robot to move through the space without hitting things? We have several papers doing this for NeRFs. The latest one is catnips, where we reason very carefully about collision probabilities. I'm not going to talk about that just because one has to choose when one has limited time. And so I'm going to talk instead about our most recent work, which is called SplatNav, just published in TRO, might be in press, I'm not sure, but it's definitely available on archive. Okay, so what is the challenge here? We all know how to plan robot trajectories through maps. The challenge is the representation of the map and the scale of the representation of the map. So GSplats are just a bunch of ellipsoidal elements out there. And so when we're planning to avoid collisions, we just plan through free space avoiding the ellipsoidal elements. But there are millions of ellipsoidal elements in a standard GSplat map. Millions. It's hard to really wrap your head around the scale. tremendous number of these things. So you have to take really strong advantage of GPU parallelized computation and as many sort of analytical tricks as you can to speed up computation. So we have a pipeline. I'll sketch it for you. It's based philosophically on a paper that came from the GRASP lab from Vijay Kumar and several collaborators called Safe Flight Corridors back in 2017. Beautiful paper. The paper considered planning through point clouds. After all, GSplats are really super fancy point clouds at the end of it. It's a point cloud marked with this ellipsoidal footprint with all kinds of visual features that allow you to render the point cloud to produce nice pictures. Okay, so what we do is we first grid up the environment, and then we, as a initialization, it doesn't have to be a super fine grid, just quick and dirty, grid up the environment, use A star to plan a path, collision-free path through that gridded up environment, and that is the initialization. You need an initialization, otherwise you're gonna end up doing far too much inefficient exploration. So you initialize a path, and then you use that initialization to carve out free space polytopes, convex polytopes, which contain the robot body and are not in intersection with any of the ellipses, any of the million of ellipses. And then you move along your pre-planned initial path, your A star path a little bit, and then you plan a new corridor. You let's say solve for a new polytope, convex polytope. And you do this going through all of the kind of straight line segments along your A star path until you've created the safe flight corridor, which is a union of these polytopes. And then you optimize the parameters of a spline, a polyspline, and then now you're off to the races. You use the standard quadrotor or motion control pipeline that you prefer. So you could use differential flatness for quadrotors. That's what we do, but you could do whatever you prefer to follow that spline. So now the real challenge mathematically is how do we solve for these polytopes super quickly? So the way we do that is there are several computational methods out there, but many of them are too slow. So we found a method that is still too slow, but reduces to a convex program. It came from this computer vision venue, kind of lesser known computer vision venue back in 2012. It basically shows that in order to find a separating hyperplane between two ellipsoidal primitives, you can cast that problem as basically maximizing a concave function. So it's a convex optimization. But the optimization variable, S, is embedded inside this matrix inverse. Turns out to be kind of slow to optimize. So in the paper, we show that you can, through some tricks, turn this into a generalized eigenvalue problem. You do some pre-computing, and then you can get rid of that inverse, that matrix inverse. You can now solve this optimization much faster. And it turns out, it's not obvious, but you can do other tricks to make it highly parallelized on the GPU. And then you're talking about the scales that are required. So here's a plot showing the number of Gaussians for which you're finding these separating hyperplanes and the computation time on a GPU. I think this is probably a 4090 NVIDIA GPU. And you see with the blue line is the original work up here. And you see, what are we getting? We're getting about 1,000 of those hyperplanes at somewhere between 10 and 100 seconds, milliseconds. This is milliseconds, between 10 and 100 milliseconds. With our various improvements, which comes down at the best performances down here, you can solve 1 million of these hyperplanes in 50 milliseconds. No, 20 milliseconds. 20 milliseconds. So we're talking about 50 hertz, basically. And so now we're in business. Now we can do this onboard in real time and replan in an MPC loop for navigation. So you might say, well, separating hyperplanes, you wanted convex polytopes. A convex polytope is nothing other than a collection of separating hyperplanes. So going back to this picture, right, each one of these faces of a polytope is a separating hyperplane. So when we're with the robots here, we solve the separating hyperplanes for the 1 million Gaussians. In fact, we also have a clever sort of KD tree data structure so that we don't have to consider all of the Gaussians. We consider a subset. But you can quickly get this polytope by enumerating the separating hyperplanes, and then the next one and the next one and so on. That's the idea. So, yes. Okay.
What do you do to the translucent Gaussians that lie within the corridor?
You said translucent Gaussians? Yeah, yeah. Yes, floaters. Yeah, right. Yeah. So that's a great question. So we don't do we don't treat these floater Gaussians in any special way. We just avoid them. So we could be avoiding a free space unnecessarily. The idea, so the idea behind this paper was that somebody else would be, we'll say, the assumption is that there's a fast online Gaussian splatting algorithm running and that we have access to a well-trained Gaussian splat. The paper itself just assumes we have access to a well-trained Gaussian splat because one needs to draw one's boundaries for a paper. But in fact, in the lab, we can run online Gaussian splatting. And what happens is when you initially start training the GSplat, you get these floater Gaussians, as you said. Some of them stretch out of the walls. Some of them just occupy free space. And you plan to avoid collisions with those. But as you move, you collect more imagery and you get closer to that space. And that imagery eliminates those false Gaussians. And then that opens up more free space and you replan. That's how it happens in practice. Yeah, sure.
KD3 that you're picking, do you update it online or do you build it from scratch?
Yeah, we build it from scratch. So let me say this in two phases. In the paper, we build it from scratch because we assume we have access to a pre-trained Gaussian splat that's static. But in fact, one would have to dynamically update that as you train the GSplat. Yeah. So so we have this working dynamically online in another paper. So I assume we can do this dynamically online. I'd have to double check with my students to know about those details. But yeah, I believe we can update the KD tree dynamically online as we train the GSplat. Although that's outside of the assumptions of this paper that I'm talking about. Yeah, great points though, very good points. So to give you a little bit of an idea of the scales that I'm talking about, these weird kind of smoke plume looking things, these are the safe corridors. So you can see the number of polytopes involved is enormous. These polytopes compose to make these really complex, elaborate sort of free space tubes. And then you plan within these tubes. And the tubes are rendered this is the same set of tubes, but from two different perspectives, safe corridors, I should say. And then here, the blue line is the execution of the robot in time as it solves its MPC. And the little green threads are the MPC paths, right? So you solve an MPC, that's your plan, and then you execute a little differently from your plan, and you replan, and so on. So you see kind of how these things work together. Great. So it's tough to find proper points of comparison for this work because this was the first to do planning in GSplats. But we compared it against the Safe Flight Corridors paper from Kumar and co-authors, where we tried, right, one has to adapt that because that's meant for point clouds. So one has to figure out how to adapt that properly. So we tried several different methods. I don't want to bore you, but the simplest way is just take the means of the Gaussians as the points. That's the fastest way. You could also sample the surfaces of the Gaussians, then you get a lot of more points. You see there's a trade-off there, right? If you sample the surface of the Gaussians, you get way more points than you need, and it becomes slow. If you sample the means of the Gaussians, you're unsafe because that's embedded inside the volume of the Gaussian, and you're going to hit things. And then you're fast, but unsafe. So there's an undesirable trade-off when porting this into the GSplats. Did you have a question?
Yeah, could I ask?
Yeah.
I don't know if you're talk later, but could you talk about what for this kind of collision-free navigation problem the GSplat representation buys you compared to a voxel grid or something? Something.
Yeah. Yeah, so it buys you, I think, all the downstream flexibility. I don't think it necessarily buys you anything inherent in terms of safety, but it allows you the ability to render these lifelike images and embed semantic codes and also segment objects of interest. And so the idea is to enable downstream flexibility. Yeah, good point, good point. So yeah, in comparing with safe flight corridors, you see this is the failure rate. So how frequently does the method fail to return a path? There's no feasible solution. And in the safe flight corridors, those are the green bars. There's fairly frequently, you do get failures, whereas ours are in blue, there's never a feasibility issue. We always get a feasible path. And then as far as the safety of the path, again, the black line is 0. So if any of the color goes below the black bar, that's a collision. So all of the other methods we tested against occasionally provoked collisions, but ours never did. Computation time, we're on par in computation with the safe flight corridor, but much faster than other methods. And then path length, similarly, we're on par with the safe flight corridor, but a lower path length than other methods. The main distinction is that with safe flight corridors, as I said, you're going to get a safety problem if you take the mean, because then you're ignoring the extent of the Gaussian. Okay, great. So now we can dovetail this directly with semantics, and we can do language commanded navigation on a pre-trained Gaussian semantic GSplat map, right? So we have a map like this. We've got embedded semantics, so we can put the command in beach ball, and we know what a beach ball looks like. But I don't see it here. Oh, it's hard to see. It's hidden behind a screen. But yeah, so then the map would highlight the beach ball, and then that would flag some volumetric Gaussians, and we take the most well-aligned Gaussian with the query, or maybe the cluster of best well-aligned Gaussians with the query, and make that the goal point, and then that initializes the rest of the GSplat planning pipeline. So here's some illustrations of that kind of semantic query. So here's the ground truth image. Here's the render, which looks very lifelike. And then here you can see the heat map indicating the alignment with the query. So this is the query's keyboard. And these alignments are contextual or associative. So anything that's associated with a keyboard is also going to illuminate to some degree. So if you query keyboard, a monitor is going to light up a little bit. A mouse is going to light up a little bit. Here's the beach ball. That's pretty distinct. Here's a phone book and so on. Here's a microwave. You get the idea. Okay, great. So let's go to some experiments. Here's the drone down here. Here's the phone book over here. That was the query. And let's play the video. And there it goes. There's no external perception at all. It's all onboard perception. We're using the modal AI drone, which I understand has its roots back at UPenn. I believe this is the latest generation of drones from Alex Kushlev and Dan Mellinger. I don't know if Dan was involved in modal AI, but I think Alex is. So they did their PhDs with Vijay and company here at the Grasp Lab. They were buddies of mine back in the day, and then they went on start some companies and worked in Qualcomm and so on, and their latest venture is modal AI. Beautiful drones. These are still the highest quality research drones you can get with onboard baked-in VIO capabilities and so on. Okay, and then the microwave from modal AI, right? Where's my mouse? And here it is again, flying to the microwave, and the microwave's down here. There it goes. Great. What have I got in time? A little bit more time. Good. Okay, so navigation, yeah, I still think there's a lot to do in terms of navigation, especially at the intersection of planning the GSplat, planning the map representation, and did I say planning? Training the map representation and producing the motion plan in sync, doing exploration, doing semantic guided exploration. I think these are the really hot frontiers in this space. So then manipulation. So, right away when my students and I started looking at NeRFs, we thought, well, this would be really great for manipulation. And it took some time to get there because there's a lot of intricacies with manipulation. In particular, manipulation is focused on objects. And so you need the ability to segment 3D spatially segment the objects away from the scene and then render motions of those objects potentially could be desirable. Reason about grasp stability and grasp placement on those objects and so on. So our work in this is called Splat Mover. And these are the students involved, John Tucker, Ola Shorinwa, and Tim Chen. I should have also called out Tim back for SplatNav. He was the main mover on the SplatNav paper. These are all PhD students of mine. Actually, Ola recently graduated, is now a postdoc at Princeton. So the idea behind this Splat Mover paper is to build open vocabulary manipulation, language commanded manipulation on top of GSplatting, enabled by embedded semantics and embedded grasp affordances. So we want the map to carry all the information that the robot needs to figure out what object is being commanded and figure out where to grasp that object. We want all of that intelligence built into the map so that the robot is basically just doing some low-level motion planning at the end of the day. And this work is composed of basically 3 modules: ask splat, see splat, grasp splat. I have 2 5-year-old twins, and so a lot of the way my mind works is in splat. They're my heroes. You know, I love how they see things so simply, and this is like see spot run, see spot play. It's just kind of like a child's decomposition of what needs to be done. So at the end of the day, the idea is to use the tools I've talked about. So we have semantically embedded GSplat map, assume it's pre-trained. But now what we're going to do is we're going to use the semantics to carve out spatially the object of interest. And then we're going to, the way that we do that in a GSplat is very simple. We just find the Gaussians that have the highest match with the semantic query and then group them together as a rigid object and then move them with rigid body transforms. And then we can render images with that motion. And it looks like the object is moving around. You can rotate it, you can translate it, you can do anything you can with any other kind of simulation software, right? But we also need grasp affordances. And so I'll talk about this in a little bit more detail, but basically just like the training process embeds color into the 3D scene and embeds semantic codes into the 3D scene, we're going to embed pre-trained affordance codes into the 3D scene. And let me see if I have more detail on that. Yeah, okay, so these affordance codes come from this model that was presented at CVPR 2023, where this is a model for images that is trained on YouTube data, basically YouTube videos of people doing things with their hands. And basically, they trained a model to predict, based on an image, which pixels a human hand is likely to interact with. That's the nature of the model. And I call it a foundation model, but it's not really at that scale. It's just kind of an experimental model, not quite prime time, but a really cool idea. So this is our pre-trained model. We didn't do this work. Somebody else did this work. We distill those features into 3D just as we do for language codes. And now we have an ability to see in the 3D volume which parts of the space a human hand would likely grab onto. So here's the semantics associated with silver saucepan. This is the semantic similarity. This is the saucepan. This is the lid of the saucepan. There's the other thing over there that was lighting up. And then here are the associated grasp affordances as distilled from this pre-trained grasp model. And you can see that they're not perfect. I would say this is promising, but certainly not the final solution to this problem. There's certainly useful cues here, but you see, it's a little bit hard to see maybe, but for example, it's telling us that the robot should grasp at the interior of the burner. You can't grasp at the interior of a burner. That doesn't make much sense. But there is useful stuff as well. For example, it's telling us roughly to grasp at the handle of the saucepan. That's what that is. The handle of the lid of the saucepan. And if I can, it's a little bit hard to see if I can orient you properly. It's telling you there to grasp at the kind of root of the handle of the saucepan as well. Not out at the end, but at the root, like close to where it meets the pan itself. So there's useful stuff in here, but it's very messy. So the way that we deal with this messiness, the semantics are not very messy. They're pretty good, actually. And the pre-trained semantic codes are excellent now, even better than what I'm showing here. So what we do is we first segment the object of interest from the semantics, extract the Gaussians. These are just the means of the Gaussian shown as a colored point cloud. So this is for a query of a drill. Extract those Gaussians. Now we have the object masked. And then we look at the affordances only restricted to that mask. So then we're not trying to grasp the burner from the interior of the burner. That doesn't make sense. We're only restricting ourselves to the object of interest. And you can see then it starts to make sense. So here it's telling us to grab the drill by the handle, which is what you want to do. Great. So then we use this object segmentation capability to plan the motion in terms of pose trajectories for the object. So if we have a command, a language command, which is like move the pot to the burner and then move the orange inside the pot, we can do that using this object-centric gsplat approach. So we carve out the pot, and then we render a series of SE3 transforms that take the pot to the burner. We also carve out the burner because we have in the language command, we have pot, we have burner, that's the object, that's the destination. And then we have orange, we carve out the orange, and we can render these 3D transforms of the orange going into the pot. Now, this is useful for multi-stage manipulation. There are 2 stages here. We move the pot to the burner, and then we move the orange to the pot, right? And the only thing the robot has is the language. Move the pot to the burner and the orange to the pot. It has to make sense of that language through the map, right? Now, if we didn't have an editable map, we move the pot to the burner, but the map doesn't know that. Suppose we don't have an editable map. The pot remains in the map where it was originally, but in the physical world, the pot is on the burner. What does the robot do? He doesn't know where the pot is. He's going to move the orange to where the pot used to be, and that's the wrong answer, right? So we need a kind of a digital twin. We need to update the state of the world to match the state of the gsplat to match the state of the world as the robot is rearranging the objects in the world. Okay, and this is a similar thing, but with a spray. Move the spray to the bin and then move the battery next to the spray. Same idea. You can see there's some artifacts at the interface between the object and the ground because there's no supervision in training the gsplat there. There's no data on what the appearance is between the bottom of the spray and the ground, right? Because they're in contact. So we've tried to use some off-the-shelf tools to kind of heal those visual scars to do some in-painting, and they work okay. But essentially, that's not the main feature here. The main feature is showing the bulk sort of geometric motion of the multiple stages. So then putting it all together, what do? We have a language prompt, pick up the drill, and move it somewhere, for example. So then we take the drill prompt and we mask out the drill, and then we find the grasp affordance heat map over the drill. And then we use an off-the-shelf grasp proposal network called GraspNet, which basically tells you, a bunch of potential pincer grasps that might work. And then we rank those pincer grasps based on their alignment with the grasp affordance to give us the best grasp, which is going to be this one right here. And then we move forward with that grasp. So that's the idea. And I'm going to show you the whole thing working. At the end of the day, you say, where's the robot? You didn't talk about a robot or robot motion planning. So for us, it's not about the robot or robot motion planning. It's about task planning. Making sense of the world and figuring out the high-level tasks. Once that's done, then the robot is just given waypoints, and then we use off-the-shelf tools to do motion planning. So here, the robot's just executing the plan. All the intelligence is really baked into the plan. Okay, cool. So great. So I talked about this idea of a digital twin and kind of keeping a record in your gsplat map of what's happening in the real world. Let's take that a little bit farther. So really what I'd love to do is have a physics simulatable gsplat. I mean, wouldn't that be amazing, right? Like something where you could really simulate the weight and the friction and the contact forces of a chair, of a bunny, of objects in the scene, of the robot itself as it's moving around in the scene. So this was the target of a work that we did quite a while ago, actually, back in 2023. It's called DANO, Dynamics Augmented Neural Object. And the idea was exactly this, is to take, in this case, it's a NeRF, because this was pre-gsplat. We can easily do the same thing with gsplats. You take an object-centric NeRF, and you tag it with properties that would be required to simulate it in a physics simulator. And then we go ahead and simulate it in a physics simulator. So this is work led by my former student, Simone Leclerc. She's now at BDAI, Boston Dynamics AI Institute. And what you're seeing here is basically a ground truth mesh in white, excuse me, simulated in a physics engine, and then our reconstructed object from a NeRF. So the object in black is constructed entirely from images. And they're both simulated in the same simulation environment, but with different contact models for simulation, because we have a custom contact model that's specific for the NeRF object representation. And you see that one mirrors the other very well. So the NeRF asset can very well represent sort of ground truth, if you want to consider the mesh ground truth. So the way this works is we take an object-centric NeRF. I'm not going to go into the details about how you get an object-centric NeRF. I already talked about how you get an object-centric GSplat, so this is somewhat similar. An object-centric NeRF, you sample points on the surface of that NeRF, and then you compute the normals of those points by looking at the gradient of the density field. And then you compute the mass by just integrating the mass over all these sample points, doing kind of a Monte Carlo integration over the mass of the sample points. The mass being the output of the NeRF radiance field, right? You get mass and you get color. You get rather density and color. And then you compute the center of mass just using the standard sort of mechanics center of mass equation. That's the black dot. And then you also get the inertia matrix, again, using the standard equation from mechanics in a Monte Carlo fashion. So this gives you all the stuff you need to simulate the object in ballistic motion. It doesn't tell you how to simulate contact. Contact is the hard part, right? So now how do we simulate contact? Suppose you have a planar surface and you're simulating contact on the planar surface. One could do many things. This was kind of an exploratory work, but I'll tell you what we did. We looked at all of the sample points that are in penetration with that contact plane. We compute kind of the barycenter of those points, the center mass of those penetration points, and we call that kind of the center of action of the contact forces. And then we have a spring damper force, which we use to model the normal force. And then we have Coulomb friction, just standard Coulomb friction law that we use to model the friction force. And the two compose together to give the full reaction force, which you see here. Simple model, really designed for you know, fast computation and sort of easy applicability to these NeRF sort of density fields. So you see here's a simulation of the bunny being thrown on the surface. You can simulate a bunny interacting with primitive shapes like spheres and capsules, or the bunny interacting with other copies of itself. So you train one bunny, but you can spawn 100 bunnies in the simulator, and they can contact each other and slide across each other and so on. Of course, not only bunnies. I hope that's clear. The bunny is just an illustration. Then you can use this model and the associated simulator for all kinds of things. You can use this for system ID to better identify these dynamics properties like friction coefficient, for example. So here we had a ground truth rollout of the bunny sliding, and then we have the simulated rollout of the bunny sliding, and we keep tuning the friction coefficient until those rollouts match. We do this in an optimization loop. Great. You can also do trajectory optimization where, okay, maybe we want our robot to push the bunny so that it lands and stops in the black circle. And then we want the robot to return to the white circle. So then you can start with a random trajectory and then again, constantly optimize against this, you know, trajectory specification until after iterations, you get the motion that you're looking for. So this is one step away from reinforcement learning, right? One could use the same principle for reinforcement learning policies. Okay, great. Now, sim to real transfer, everything I showed you so far was in simulation. The NeRF of the bunny was trained from a mesh rendering of the bunny, which is a bit of a cheat, although it's quite common in the computer vision world. I think in robotics, we want to make sure we're dealing with real world images, real world things. So we took data sets of a box sliding and of a bottle rolling, and then we did this exercise to basically fine tune the motion parameters, the friction coefficient, mass, and all this stuff of the dynamics augmented NeRF so that it represents the real motion seen in the world. So the white renderings are without the fine tuning of the parameters, and the brown gray renderings are with the fine tuning of the parameters, and then the black renderings are the actual ground truth data. A little bit hard to see on those videos. Apologize for that. Okay, so we're going to wrap up real quickly. So great, I'm hinting at now training policies with these models, thinking about these models as kind of simulators through which you can train policies. Why do we need a new simulator? We need a new simulator because this simulator can provide a really high fidelity visual information, and you can interact with the simulator semantically, right? That's the power here. So what we did, this is work by my student Junen, who's finishing up his PhD. We train a GSplat of our whatever environment where we want our quadrotor or robot to fly in or to move in. And then we embed a pretty low fidelity dynamics model of that robot, and then we can render sort of dynamically feasible image trajectories, if you like. So like a sequence of images that would be seen if the robot were to fly as a quadrotor flies. And then we use those images and the associated actions to train a policy, which you see here. And that policy we've shown can transfer zero shot to the real world. So the drone has never flown in the real world, has never seen real world images, only simulated images from the GSplat. But this is the real drone flying the same trajectory that you saw in that simulation on the left, but now it's flying it in the real world. All sensing on board, all compute on board, no strings attached. So the drone is fully autonomous here, navigating through the world. So the way we do this in a little bit more detail, and I know I'm running late here, I'm going to finish up quickly. So again, we do casual video capture of the room. We don't need to fly through the room. We can do this with a handheld camera. Train the GSplat models, all standard stuff. It can be done in a matter of minutes. And then we integrate low fidelity and sort of 9-state dynamical model, so a semi-kinematic, semi-dynamic model of the drone, where the low-level commands are body rates and force, body rates and thrust, which is the same commands that a human pilot uses in drone racing. So we're able to access the kind of high dynamic agility of the drone, but it's still a fairly low fidelity model from a dynamics perspective. And then we can render dynamically feasible trajectories of the drone, what the images would look like if the drone were to fly. And then we pair that with a standard trajectory planning pipeline. So waypoints, spline, differential flatness, all the stuff we all know about, to get basically control actions for the drone in simulation to execute this trajectory. Now we have the control actions and we have the images that will result from those control actions. You could think of this as a student-teacher learning paradigm. So we're designing the teacher, the expert teacher, with privileged information because it's in simulation. Then we randomize like crazy. So we disturb the drone along its trajectory in all kinds of ways, and then supervise the recovery trajectories to get back onto the nominal trajectory. We also randomize over mass properties, thrust properties, battery properties, every property we can think of. It's free. So G-splatting can render these images at 100 hertz. So go crazy. There's no reason not to produce lots and lots of training data. So that's what we produced 300,000 image action pairs to train this neural network. And then that's it. Then it's basically supervised learning. So we have the images, we have the actions, and we train through a supervised learning sort of regression to get our policy to imitate the actions given the images. And then we can deploy in the real world zero shot. So the real trick for this zero shot deployment is two things: this high degree of domain randomization in the simulator with a very lifelike imagery produced by the GSplat, but also this other trick, which turns out to be really essential. It simply doesn't. We tried it without this module. We tried a lot of different, this was a year of work, basically, of experimenting in different combinations of modules. And you need this thing called rapid motor adaptation, which is basically a way of producing online adaptation in a pre-trained, learned policy model. This seems to be the secret sauce for making pre-trained models trained in simulation transfer to the real world. This idea was introduced first by Jitendra Malik's group at Berkeley a few years ago in the context of quadruped locomotion. It's seen its way into a few other robotics works, but we found this to be really, really important. We made some modifications and so on for the quadrotor domain, but basically the idea is that you train this special module. It's basically an encoder that takes in a brief history of IMU data and a brief history of control inputs, and learns through supervised training in a simulator to map that data history into parameters of the vehicle. That's the hard thing that you never really know in the real vehicle, right? So aerodynamic parameters, the battery drains. Anybody who's worked practically with drones knows the battery drains. What worked well 5 minutes ago doesn't work at all anymore. You need a way of adapting to these things. When you fly close to a wall, your thrust parameters change. Close to the ground, all your parameters are constantly changing. So this module, this beautiful little module, basically learns to map a data history to these parameters, and then gives those parameters to what we're calling the command module, this final multi-layer perceptron. So then this is paired with a ResNet pre-trained squeeze net, which is basically takes the images and encodes that into a feature vector and then some other multi-layer perceptrons that basically do something similar to VIO. And then finally, all these things go into the command network to issue the commands. Okay, so we can put all of this, the neural network, all of it, and the sensing goes onto a drone. This is our own in-house drone. This isn't the modal AI. And it can run on an Orin Nano board at 30 hertz. So these forward pass inferences required for the online control can run at 30 hertz. So I'm almost done. I know I'm out of time. So we get 0-shot sim-to-real transfer, as I said, but it's more than that. We get like really great robustness. This was just from an empirical point of view is really surprising. So we noticed how robust this was early on, and then we said, let's just go wild. All you guys get in the lab, do whatever you want to try and mess this thing up. Mess up its visual field of view as much as you can. It doesn't seem to care. It knows how to cue into the objects that are there that are similar to what it was trained on and to drive its motion based on those objects. So wind gusts, mass changes, plus 30% mass changes, dim the lights by 50%. This was a concern because it's trained to expect certain images, but it turns out it's also quite robust to dim lighting. Move the furniture items around. It doesn't seem to care. It can cue in on the furniture that is still where it was during training and ignore the ones that have moved. I'm not claiming I know why or how, but this is just empirically what happens. And then dynamic distractors, which are the knuckleheads, my PhD students running around in the lab trying to mess things up. Okay, finally, last slide. How do we now embed semantics? I think this is really exciting. We can get a drone, all the compute and all the sensing on board to navigate in a visual environment. Now, how can we get it to understand our commands? So what we're going to do, this is work that is unpublished, but looks promising. We're going to not do too much. We're trying to use a trick. So we talked about clip. What we're going to do is at runtime, we're going to take the language query that comes in at runtime, like fly to the microwave. We're going to take the image stream at runtime. We're going to take the clip similarity, and then we get a heat map. Instead of a RGB image, we get a heat map image, which is a semantic relevance image. And we're going to just train, we call this model sous vide, by the way. It's an acronym. I don't remember what it stands for, but sous vide is this cooking technique that where you cook meat under a vacuum sealed package so that you can cook it in a very controlled way. And I like the metaphor because we're cooking the policy in a vacuum sealed GSplat package aside from the real world, and then we can control it very carefully with lots of randomization, domain randomization. So sous vide. So then we're cooking the sous vide policy, but now the policy learns to understand semantic relevancy maps without having to understand semantics. It doesn't even know what the language command is. It just gets a heat map. And so the power of that is you basically get semantics for free. So it learns to navigate based on the heat map, regardless of what the goal is. So here, the goal was the microwave, and you navigate to the microwave. As far as sous vide is concerned, it's just going to the hottest point in the volume. It learns how to navigate through the space and avoid obstacles so that it images the hottest portion of the space. So you get microwave, you get computer. Here it is navigating to the computer. You guys get the idea. And this is work led by Max Edding, my PhD student. Okay, let's go ahead and wrap up. So yeah, I think you guys can see I'm super excited about this space. I think, baking intelligence into world models for simulation, for semantic understanding, and for scene editing I think there's a lot of promise there in driving forward robot autonomy. And I think there's so much more work to be done. So thank you all, and thank you, of course, to my incredibly talented team of PhD students who are the real brains behind the work. Also, I collaborated on several former GRASP members. Philip Dames is now a professor at Temple, but he did his PhD here. Monroe Kennedy is professor at Stanford. My colleague, I work with him frequently. He did his PhD here. So GRASP has had a strong impact and continues to have a strong impact on me and the entire robotics world, no doubt. Okay, thank you all for your attention, and happy to take any questions. Little bit over. We have a few questions.
Hi. I just have a quick question. I thought the NeRF to the mesh extraction and physics embedding was super interesting. Have you looked into using that for pulling a mesh scene? And do you think that would be redundant with your current approach, or is there like big obstacles from doing that?
So, if I understand you right, you're asking if we can basically extend the work that I showed with the bunny and the dynamics of the bunny to a full scene. Is that what you're asking? We're kind of working on this, but from a very different perspective. So firstly, just to clarify, in what I showed, there was no mesh. I mean, I was using the mesh as a ground truth, so that I had very careful control of geometry and so on. But the dynamics that I was rendering were entirely on NeRFs and sample points sampled from NeRFs. So there was no mesh. But basically what we're doing for whole scene reasoning and whole scene sort of dynamics is to build the same concept on GSplats, but then learn a transition, a dynamical transition conditioned on robot actions as a transformer, pre-trained with lots of scenes. So the idea is, the dream is to be able to ingest lots of video data, train GSplats from the video data, and then use those GSplats to train the transition function of a transformer. And that transformer then becomes like your simulator. And then in a novel scene at runtime, you have your GSplat, and you can then forecast by running the transformer on action plans to see what might happen in the future. That's what we're working on. Yeah. Yeah.
Thank you. So I have a question that I'm guessing you get a lot in Stanford, which is why should I do all of this? I mean, why not big model, language, whatever 3D is needed is gonna get into the model. So I'm curious, what are your thoughts about this?
Yeah. Thank you. I love that. You're right, and I do get that question a lot, and I think it's a perfectly fair question. So I think there are two emerging, from my point of view, two emerging paradigms in this highly AI-centric robotics that's emerging. One is what I've talked about, where all the intelligence is baked in the map, and then you sort of modify existing modular robot autonomy pieces around this more intelligent map. The other paradigm says there is no map, there is no modularity, there is no traditional autonomy stack. It's just images or raw perception and raw actions and a big transformer between the two. So you might call this generalist robot policies. Examples are the RT models, RT1, 2, and 3 robot transformer that came from Google Robotics and Stanford, and then OpenVLA more recently, and now Pi0 from Physical Intelligence, which is Chelsea Finn and Sergey Levine's company. I mean, they're showing super cool stuff. I don't know how well it works. We're trying to spin those models up in my lab. I have some doubts. I really like modularity. I don't know. I mean, I'm trying to hedge my bets and put my research dollars, so to speak, in both camps, because I think they're both really interesting. I think maybe the right answer is somewhere in the middle, where you can still preserve some spatial intelligibility, and spatial interpretability, and you can still preserve some degree of modularity. I think the modularity is really nice for safety, for debugging, and for explaining to stakeholders in downstream when you're talking about deployed robot technology. Why did my car drive off a cliff? I don't know. The transformer did it. I don't know. You want some, the signal there did something funny. It saw an image it didn't expect. There was a deer in the road. You want some way of diagnosing when things go wrong and then improving the system later that's a little more subtle than just throw more data at it, right? So I think the modularity that's offered by the paradigm I'm describing here is really attractive. But then also the efficiency of the end-to-end just images to actions is also really attractive. And I mean, what Pi0 shows with this clanky, garage-built, bimanual manipulator folding laundry, not only opening the door, taking the laundry out, putting it on the table, and folding piece by piece for like 45 minutes uncut. It's mind-blowing. So there's definitely something powerful there. But I mean, how many takes did that require? I don't know. What happens if the laundry falls on the floor and it's never been trained for that? I don't know.
I had a question about like the multi-agent thing. I remember you talked a little bit, like mentioned briefly about like that hammer paper.
Yeah.
I was wondering like what sorts of things are you doing to combine the neural radiance fields and this research with like multi-agent.
Sure, thanks. Yeah. So Hammer, I'll talk a little bit specifically about that. Yeah, I mean, my lab's called the Multi-Robot Systems Lab. Traditionally, I've always done collaborative robotics, mostly from a control theory perspective. And I always considered this, what I presented as a temporary detour, building enough maturity in these tools so that I can come back to the multi-robot paradigm, because I think that's still really cool and really powerful. So Hammer was it's a very recent paper. It's still under review. Basically, what we did is we spent a lot of time thinking about how should we really do distributed robotics, or let's say multi-robot systems, asking the question, what should be distributed and what should not be distributed? So let me get to the point. These models all require large GPU workstations, and no time soon are those workstations going to live on small scale devices, right? They're not going to live on devices like wearable, AR, VR units. They're not going to live on drones, maybe someday in the future, but not right now. So we're not going to train the NeRF of the GSplat on our AR, VR unit or on our drone. We just don't have the technology. So what we do is we do lightweight VIO or SLAM on device to get the images tagged with the camera poses. And that works well, and that's reliable, and that can run on device at real time. Then we communicate the images and the poses back to the GPU workstation. And then what do we have? We have a bunch of unaligned world frames. And so now the problem is to find the alignment from a new device to the existing, say, master world frame. And that's really the meat of the problem. So Hammer is basically that. It's saying, suppose we have 3 devices already working together, already agreeing on a world frame, and already building a GSplat, and that GSplat lives on a GPU machine. And then we have a new device which connects to the GPU machine and starts streaming images and camera frames. How do we orient the images and the camera frames into the existing map to get the transform between the local world frame and the global world frame? And then once we have that transform, we stream in and just train the GSplat centrally. That's the idea. And we do that alignment in a coarse plus fine alignment procedure, where the coarse procedure subsamples some images from both the global set and the local on-device set, and then uses some semantic cues and structure from motion to do coarse alignment. And then we do gradient-based fine-tuning once we found that coarse alignment. And we continue the gradient-based fine-tuning throughout as part of the NeRF training process. So we do the one coarse alignment to kind of snap the local frame into the global frame, and then we continually refine as new data streams in, so that we're kind of, you could think of it like loop closure, right? As the loop closure happens because as the device goes around and sees a part of the map that another device has seen or that it has seen, so the global workstation sees the new image and anticipates an old image and says, oh, we need to bring these into alignment. And that's basically a loop closure. Yeah.
All right, I think we're out of time.
Okay.
Please join me in thanking Professor Max Schwager again for his wonderful talk.
Appreciate it.
I know there were a lot of questions we weren't able to get to, but Professor Schwager will be having lunch up in the main grasp lab. Aurora Chen and Yuezhan Tao will be taking him up there. So if you want to continue to engage with him on these conversations, feel free to join them up there. And please tune in next Friday for our next Grasp on Robotics talk featuring Reed Simmons from Carnegie Mellon. If you want to see any of our previous talks, of course, please check online. Thank you.